The quest to visualize the fourth dimension is one of the most captivating and challenging endeavors in both mathematics and art. It is a journey that forces us to confront the fundamental limitations of human perception, to stretch our minds beyond the familiar confines of height, width, and depth, and to imagine a reality that is fundamentally beyond our sensory experience. The Tesseract, or four-dimensional hypercube, stands as the most iconic symbol of this quest, a shape that has captured the imagination of mathematicians, artists, and the public alike for over a century. It is a shape that we cannot see, cannot touch, and cannot truly comprehend, yet we have developed a rich and multifaceted tradition of representing it, of creating visualizations that serve as windows into a higher dimensional world. From the early conceptual models of Victorian mathematicians to the stunning computer-generated animations of today, the history of Tesseract visualization is a testament to the power of human creativity to render the invisible visible and to make the impossible, if not fully graspable, at least tangibly imaginable. The story begins in the late 19th century with Charles Howard Hinton, a British mathematician whose fascination with the fourth dimension led him to develop some of the first systematic methods for visualizing a tesseract. Hinton, who actually coined the word tesseract in his 1888 book A New Era of Thought, was convinced that the human mind could be trained to perceive higher dimensions. His approach was one of intense, systematic training. He devised a system using a set of 81 small, color-coded wooden cubes. By memorizing and mentally manipulating the shifting configurations of these cubes, an individual could, Hinton believed, develop a direct feeling for what a four-dimensional object would be like. It was a form of mental gymnastics designed to break the mind free from its three-dimensional habits. His methods were so elaborate that they required a staggering 81 different colors and an equally bewildering set of Latin names for the various parts of the tesseract. Hinton's work was not just an intellectual exercise. It had a profound philosophical and almost spiritual dimension. He believed that gaining an intuitive perception of higher space required one to cast out the self, to rid one's mind of the ingrained concepts of right and left, up and down that are inherent to our position as observers in a three-dimensional world. Hinton's influence on the visualization of the tesseract was profound and long-lasting. In his 1904 book, The Fourth Dimension, he provided detailed diagrams of the tesseract, which were among the first visual representations of the shape to reach a wider audience. These diagrams, which showed the complex, interlocking structure of the hypercube, were a revelation to many readers. They offered a glimpse into a world that was previously only accessible through abstract mathematics. Hinton also proposed a set of physical models for studying the tesseract, a set of 27 cardboard slabs, a set of 81 one-inch monochrome cubes, each a different color, and a set of 12 multicolored Catalogue cubes. These models were sold commercially, allowing anyone with 16 shillings to purchase a set of 81 cubes and 27 slabs and begin their own journey into the fourth dimension. In a wonderfully unexpected twist, Hinton's work on visualizing the fourth dimension also led directly to one of the most ubiquitous pieces of playground equipment in the world, the jungle gym. At home, Hinton built a real, climbable multi-cube frame from bound bamboo sticks for his children, a structure that was later adapted by a progressive educator into the first permanent jungle gym. Following Hinton, the visualization of the tesseract entered a new era with the advent of computer graphics. In 1966, Michael Noll created the first computer model of a hypercube, a wireframe representation rendered on a computer screen. This was a watershed moment, as it demonstrated that computers could be used to generate images of objects that were fundamentally beyond human perception. It was the beginning of a new visual language for higher dimensional geometry. In 1978, Thomas Banchoff, a mathematician at Brown University, developed a custom computer graphics system that allowed for real-time, interactive computer animation of a hypercube. He also created the film, The Hypercube, projections, and slicing, which provided a more complete viewing of an animated hypercube, showing it rotating, projecting, and being sliced by three-dimensional spaces. Banchoff's work was revolutionary because it made the tesseract not just a static image, but a dynamic, interactive object that could be explored from different angles. He used the system to generate a series of stunning visualizations that were used to teach geometry to students at Brown. The mathematical principles behind these visualizations are elegant and powerful. The standard method for visualizing a tesseract involves a two-step projection, first from 4 dimensions to 3, and then from 3 dimensions to 2. The first step is a perspective projection from 4D to 3D. This is analogous to how a 3-dimensional object casts a 2-dimensional shadow. The mathematical operation involves taking the 4 coordinates, x, y, z, w, of each vertex of the hypercube and projecting them into 3-dimensional space. One common method is to divide the x, y, and z coordinates by the w coordinate, which creates a perspective effect where objects farther away in the 4th dimension appear smaller in the 3D projection. The second step is a similar projection from 3D to 2D, which allows the image to be displayed on a computer screen or printed on a page. To create a sense of depth and motion, the tesseract is rotated in 4-dimensional space. This is done by applying a 4D rotation matrix to the vertices of the hypercube. The rotation matrix is a 4x4 matrix that maps the 4D coordinates of the vertices to new 4D coordinates. By rotating about different planes in 4D space, such as the XW plane or the YZ plane, the tesseract can be made to appear to twist and turn in complex ways. The result of this process is the classic, mesmerizing animation of a tesseract, a complex, wireframe structure that seems to fold in on itself, its internal structure passing through its own surfaces in a way that is both beautiful and deeply counterintuitive. The tesseract has also been a powerful source of inspiration for artists, designers, and filmmakers. One of the most notable artistic depictions is the kinetic sculpture, Round About 4 Dimensions, by Julius von Bismarck and Benjamin Mauss, which is on permanent display at the CERN Science Gateway in Geneva, Switzerland. The sculpture is a physical, mechanical representation of a tesseract. It consists of a series of rotating, interlocking geometric structures that cast constantly changing shadows on the surrounding walls. The artists explain their work by saying, when a 4-dimensional body rotates, its 3-dimensional shadow seems to invert. Here, that abstract notion is made a visible reality. The sculpture is a powerful example of how art can make abstract mathematical concepts tangible and accessible, allowing viewers to experience the idea of a higher dimension through a direct, physical encounter. It was commissioned by CERN, the European Organization for Nuclear Research, as part of their Science Gateway, and it stands as a testament to the link between art and science, and the power of visual thinking to illuminate the deepest mysteries of the universe. In popular culture, the tesseract has become a pervasive symbol of the mysterious, the powerful, and the incomprehensible. It has appeared in various forms in films, literature, and video games. In Marvel Studios films, the tesseract is a powerful cosmic artifact, often depicted as a glowing blue cube. In Christopher Nolan's Interstellar, a tesseract is a location inside a black hole, used for communicating with the past. In Madeline L'Ingle's A Wrinkle in Time, the tesseract is a concept used for space-time travel. These cultural references speak to the power of the concept. The tesseract has become a shorthand for things that are beyond our normal understanding, a visual metaphor for the limits of human perception and the vast, hidden complexities of the universe. The depictions of the tesseract in these works are not always mathematically accurate, but they are evocative and powerful. They tap into a deep-seated human fascination with the unknown and the desire to explore worlds beyond our own. The digital age has brought tesseract visualization to a mass audience. Today, there are countless online tools, apps, and open-source code repositories that allow anyone to create their own tesseract animations. GitHub, for example, hosts numerous projects that use programming languages like Python and Pygame to create real-time visualizations of a rotating hypercube. One project, Tesseract Simulation, uses Pygame to apply 4D rotation transformations and project the result onto 2D and 3D spaces, visualizing the process in real time. Another project, Hypercube, provides a simple visualization using Pygame with interactive controls for toggling rotation axes and changing rotation direction. The project, Tesseract Animation in Blender, uses the 3D modeling software Blender and a Python script to create a stunning, dynamic visualization of a tesseract that can be rendered and animated. These open-source projects democratize the creation of tesseract visualizations, allowing anyone with a computer and some basic programming skills to explore higher-dimensional geometry. They are a testament to the power of open-source collaboration and the accessibility of computational tools. The field of 4D visualization continues to advance with new research and development. A 2026 paper in the journal SoftwareX describes Viviani 4D, a Python framework for the exact representation and interactive visualization of 4D algebraic hypersurfaces using NURBS, non-uniform rational B-splines. The framework is designed to maintain mathematical exactness while providing an intuitive interface for generating continuous families of 3D surfaces from a single 4D model. It is a significant step forward for researchers and educators in computational geometry, CAD, and scientific visualization, as it allows for the exact representation and manipulation of higher-dimensional objects. Another 2025 paper in the Journal for Geometry and Graphics presents a geometric approach to creating visualizations of 4D algebraic hypersurfaces by finding shadow boundaries and occluding contours in a 4D perspective. The authors use polynomial equations to construct components of a 3D model of a scene image, which can be plotted by standard computer algebra systems. This method preserves many properties of the visualized shapes, making it suitable for precise mathematical or scientific visualization. These academic developments demonstrate that the visualization of higher-dimensional geometry is not a closed chapter, but an active and evolving field of research, with new techniques and tools being developed to push the boundaries of what we can see and understand. The Tesseract, the four-dimensional hypercube, is far more than a mere geometric curiosity. It is a powerful symbol of the human quest to understand the universe beyond the limits of our senses. From Hinton's colored cubes to the latest computer graphics, the effort to visualize it is a testament to our determination to grasp what is fundamentally ungraspable. It is a journey that has challenged mathematicians, inspired artists, and captivated the public imagination for over a century. The Tesseract is a reminder that the universe is far stranger and more complex than we can possibly imagine, and that the greatest adventures are often not outward, into space, but inward, into the vast and uncharted territories of the human mind, where the impossible is not an obstacle, but an invitation to imagine. It is a testament to the power of visual thinking to illuminate the darkest corners of the cosmos and to make the invisible, if not fully visible, at least tangibly real.